So we're about to start chapter 6, which is on linear transformations. When you hear the words linear transformation, I want you to think about kind of like a function where we're putting something into a function and we're getting something out of the function. So we're going to talk about things like inputs, outputs. Domain and range is something that we're familiar with functions. Domain is a set of items you put in. The range is a set of items that comes out. But I want you to think about it as kind of like a roadmap too. It's a way to take you from one space, whether it's an R2 or R3 or a subset of those, into another space. So it's kind of like a map. It gets you from one world to another world. So let's start by looking at some terminology. The standard function terminology is used for such functions. For instance, V is called the domain of T. So those are your input items. What kind of things can I plug in? W is called a codomain. Now that's a new term for us. I want you to think about the codomain as what can you possibly get out of this? Our definition of a domain is the same as it is from functions. It's that thing that you're plugging in. The codomain consists of things that you can possibly get out. Now, the range is actually what you are getting out. The set of all images of vectors in V is called the range of T. So the range is what you actually get out. So if we're talking about all of this in terms of a picture, so we have a space here, we're calling it V, and this item, lowercase v, lives there. And we have some kind of mapping, and that mapping will take us to this other place, okay, which is that codomain. Okay, but we may not hit everything in that codomain. What we're going to hit lives in the smaller space. That's a small subset of that codomain, and that's called the range. So the range is what you're getting out. The domain's what you're putting in. The codomain is a set of things that you could get out. So let's kind of look at an example over here. So I've drawn this on my sheet. This is an example of domain, codomain, and range. So let's say we have this set A and this set B. And A consists only of the numbers 1, 2, 3, and 4. And I'm looking at a mapping where Y is equal to 2x plus 1. So if I were to plug 1 in, I'm going to get the number 3. If I plug 2 in, I'm going to get the number 5. If I plug 3 in, I'm going to get the number 7. And if I plug 4 in, I'm going to get the number 9. Now, we could plug different numbers into this, and we could find a way to get the number 1 out, and find a way to get the number 2 out, and find a way to get to number 4 out, and so on. But what I'm actually plugging in, I'm limiting my domain to just these values, which means I'm not going to get all rows out of here. I'm only going to get a select few values. So my domain consists of the numbers 1, 2, 3, 4. Our codomain is everything that's in the second set B. So that consists of the numbers 1 through 10. I'm going to abbreviate that way. But the range is what we're actually getting out. Because we have limited this domain to just 4 values, that means we're only going to get 4 values out here. So our range consists of just these numbers 3, 5, 7, and 9. Now, this is an arbitrary picture. We could have drawn it differently. The domain and codomain would look different based on the picture. But if you had this given picture under this image and you're using just these values, what would come out? And that's what would come out. So now let's talk about some other definitions. Let's talk about image and pre-image. So when we talk about the image of a transformation, we're talking about what are we getting out when we plug these values in. So let's look at example 2. So we have this transformation, and they're using the notation T here to signify a transformation. And we're taking a two-dimensional vector, v1 and v2, and when we transform that, we're going to get a three-dimensional vector. So our first component is going to be 2 times v2 minus v1. Our second component is v1, and our third component is v2. So if we're talking about the image of v, we're going to plug in that 0, 6. Where does 0, 6 go under this transformation? That's what we're asking. If we were to plug that in, we're getting 12, 0, and then 6. So that's your image. That's where it heads to. This guy will end up being in the range of this transformation. Now B is asking us for a pre-image. Pre means before. So what did this vector look like before? That's what we're asking now. So when we substitute in v1 and v2, oops, 2v2 minus v1, v1 and v2, we end up getting 3, 1, and 2. So that means that this component, 2v2 minus v1, has to be equal to 3. v1 has to be equal to 1, and v2 has to be equal to 2. So we know what v1 and v2 are. We just need to make sure it satisfies this. So if we make a substitution here, and we do get 3 is equal to 3. So that means v1 is equal to 1 and v2 is equal to 2. So our pre-image would be the vector 1, 2. And what that means is that if we were to plug this guy into this transformation, we would get that piece out. That's what it means to be a pre-image. What did it look like before? Let's look at number 6. So look what's going on here. We have a transformation in R3, and we are going to something that is in R2. A is asking us for the transformation of 2, 1, 4. If we were to substitute that in here, we're going to have 2 times v1 plus v2 for the first component, and then v1 minus v2 for the second component. So that's going to be the vector 5, 1. That's your image. That's what this guy looks like under that transformation. It takes something from R3 and it goes into R2. Now they're asking us in part B to find the pre-image. So if we were to apply this transformation, we're going to get the vector negative 1, 2. So set up a system. Solve. I got 1/3 and negative 5/3. So that tells me my V1 and V2 would be 1/3 and negative 5/3. So what that means is if we were to take this vector and apply this transformation, we will get this vector. But let's be careful here. So notice that we should get something in R3, right? But we only ended up with something in R2, V1 and V2. So what does that tell us about that third component? Well, that tells us that third component could be anything. I'll write C here. Or C can be any number. So you got to be careful with that too. Just because their system only had 2 equations and 2 unknowns, because we have to have something in 3 dimensions, right? We're looking for V. We have to think about what would that third component be. And in this case, it doesn't matter. That third component is not used to figure out what that first or second component would be for that result, that image of V. So it could be anything. So that takes us to our definition of a linear transformation. What is a linear transformation formally? So we're going to let V and W both be vector spaces. The function t, that's your linear transformation from V to W, is called a linear transformation of V into W when the following 2 principles are true for every vector U and V and for any scalar. So if we were to apply the transformation to the sum of U plus V, that would be equivalent to applying the transformation to U, applying the transformation to V, and then adding them together. That's what the first piece of the definition says. The second piece says the transformation of a scalar value times U is equivalent to the transformation of U multiplied by the scalar value. So let's do an example where we're going to show that we have a linear transformation. So let's say we have a transformation. This is going from R2 to R2. And we want to prove it's a transformation. So we need to come up with a couple of vectors. So we're going to let U be U1, U2. And V be V1, V2. So then when we add U plus V together, we're going to get U1 plus V1 and then U2 plus V2. This guy's taking something from R2 and going into R2. So we need to start with, let's prove T of U plus V is equal to T of U plus T of V. That's our first piece. So we want to do the transformation for that sum. So I'm going to write this using this notation. So that's U1 plus V1, U2 plus V2. Now think about what this transformation is saying. Under this transformation, here's my first and second components. My new first component would be the difference of the two. My new second component would be the first component plus 2 times the second. So let's write that in here. So I'm going to use that transformation, which means I do not have a t in front. So this is first component minus the second. Our first component is U1 plus V1 minus the second, which is u2 plus v2. And then our second component is v1, which is that first piece, u1 plus v1, plus 2 times the second piece. So I am literally picking this up for that first piece, and this guy is going into my second piece. So let's do some fancy math here and simplify this. So we've got u1 plus v1 minus u2 minus v2. u1 plus v1 plus 2u2 plus 2v2. So I'm going to do some grouping here. u1 minus u2 plus v1 minus v2. u1 plus 2u2 plus v1 plus 2v2. And now I'm going to group all of the u terms into one transformation, or into one vector rather. Let me talk about it that way. And then I'm going to group all the v's into another vector. So notice that if I were to add these two vectors together, I will get that previous step. So everything we've done is legal. Now, this guy would be the transformation of u. If we were to apply this transformation to this, we would have this piece. And if we were to apply this transformation to v, we would get that. So that is the transformation of v. So we have proven that t of u plus v is equal to t of u plus t of v. Now we need to prove the second. And that says t of cu has to be equal to c of tu. So let's start with t of cu. I like to draw what that's going to look like. U is u1, u2. So that would be t of cu1, cu2. So now we're going to apply that definition. So I'm going to go back up here so we can see it a little bit better. Here's the definition. Just kidding. Here's the definition. I wish my screen was just a little bit bigger. So the definition says it's going to be first component minus second component. And then first component plus 2 times the second component. Here's my first component. Here's my second component. So we're just plugging those into that definition again. Now notice we could factor a c out of those terms. And notice we could factor a c out altogether. And this guy is the image of vector u under that definition. So that is t of u. So we have proven that second axiom in the first one, which means that this does satisfy that definition. So therefore, we do have a linear transformation. I'm going to abbreviate transformation that way. Piece of cake, right? So I want you to pause the video, take a few minutes, and I want you to look at 9, 11, and 17. See if you can figure out whether or not you have a transformation, a linear transformation, or whether it's not a linear transformation. You can go through the process and see if you can prove it. So let's look at that first one. We have a transformation from R2 into R2, and the transformation for xy will go to x, and the y coordinate, that second component there, is always going to be 1. So if we want to prove this, this is where we're going to start. And you may already see that this is just not going to work out. So we're going to let u be u1, u2, and v be v1, v2. So then u plus v, I do like to go ahead and add these together. So t of u plus v. Under this transformation, I'm doing the sum. So this is going to be u1 plus v1, u2 plus v2. Under this transformation, this is going to go to u1 plus v1. That first component goes to the first component. Y is always going to go to 1. So this one I'm going to approach a little differently. Now I'm going to look at that right side. If we were to apply the transformation separately, so t of u1, u2 would go to u1, 1. And t of v1, v2 would go to v1, 1. And if I add these together, I do get u1 plus v1 for the first component. But notice I get 2 for the second component. So that's the problem. This guy fails that linear transformation, which means no, this is not a linear transformation. We look at 11. We are going from R3 to R3. We're looking at the transformation xyz is equal to x plus y, x minus y, and then z. So I'm going to come up with 2 generic vectors again. So u plus v is u1 plus v1, u2 plus v2, u3 plus v3. So the first thing we have to show is t of u plus v is equal to t of u plus t of v. So t of u plus v would be t of that sum apply the definition. So we're going to have first component plus second component. First component minus second component. And then third component. So let's do some fancy math. So I'm going to do some rearranging here. I'm going to group my U terms together. Plus, and then group my V terms together. And we can see this is the transformation of U, and this guy is the transformation of V under that definition. So that first axiom works out fine with no problem. If we look at the second axiom, so CU would be applying the transformation for CU1, CU2, CU3. Substitute in to this definition. It says first component plus second component. First minus second, and then third. Notice we could pull a C out. So that is equal to C times the transformation of U. So we have satisfied both axioms, therefore we do have a linear transformation. And then with 17, we're looking at taking something in M22 and taking it just to a real number. So the transformation of matrix A would take A plus B minus C plus D. So we're just adding or subtracting the values of the items in matrix A. So let's let A equal A, B, C, D, and B equal, let's just do E, F, G, H. So T of U plus V. Let me change this to A plus B. Equals the transformation of, now that sum would be A plus E, B plus F, C plus G, and D plus H. So under this definition, we're just going to add A plus E. So there's first component plus the second component, which is B plus F, which was here. And then we're going to subtract the third, minus C plus G, and then add the fourth, plus D plus H. So that's equal to A plus E plus B plus F minus C minus G plus D plus H. So now I'm going to regroup. So there's our terms from the first matrix. And then there's our second matrix. So this is the transformation of A plus the transformation of B. So our first axiom is fine. Now let's look at the second axiom, which says T of CA has to be equal to C times TA. Instead of C, since we've already used C, I'm going to use lambda. So we need the transformation of lambda A, lambda B, lambda C, lambda D. Under this definition, is going to be lambda A plus lambda B minus lambda C plus lambda D. And we see that we could factor a lambda out of each piece. And that's equal to lambda times the transformation of matrix A. So we have also satisfied that. So therefore, yes, this guy is a linear transformation.